Thank you. It's a pleasure to be here. I'm a little scared because it seems a little too organized. But I don't know. It goes against my principles. But so yeah, I'll be talking about just some random facts about Galois groups. Well, sort of. So the basic question is, well, there are many ways to ask how you take polynomials and they have Galois groups, and the question is how are they distributed? So the question is how they distribute with respect to what? And the simplest model, the most primitive model, is, well, first of all, because we're simple people, and I'm so simple I don't understand rational numbers, our polynomials will be monic, and they'll have integer coefficients. And then, how do you make a set of polynomials? Well, there are infinitely many of them, so you have to somehow select, compare, and contrast. So the first coefficient is 1, and the other ones are between negative n and n. So this gives you a set of 2n to the degree of the polynomials. And as n goes to infinity, you say how many Galois groups are there of a certain kind. So, oh, that's actually me. OK. I'll ignore it and hope it goes away. So mankind, in infinite wisdom, figured out a long time ago that generically the Galois group is as big as it could be. So I'm not sure if it's actually. So I think the first person who is not mentioned in the slides, therefore I'll just keep talking, I think was Abel, who I think, you can correct me if I'm wrong, I think Abel did the function field case, right? His coefficients, you look at the polynomial with coefficients being variables, then the Galois group is a Sn. Yeah. And then the next step, I guess, was Hilbert with his irreducibility theorem that says that most specializations will have Galois group Sn. But this was ineffective, as far as I know. So the first effective result that I'm aware of, and the fact that that's the first I'm aware of doesn't mean it was the first one, was due to van der Waarden. And I think the paper is in 1936, although I've had some arguments about this, who tried to make this result effective. So how does his argument work? So the first observation is, I think it's a theorem of Dedekind. Look at the prime, factor your polynomial mod p, and you'll have some degrees of factors. Degree 7, 3, and 1. Dedekind shows that means that the Galois group contains a permutation which has a 7 cycle, a 3 cycle, and a 1 cycle. Okay? So we know the conjugacy class of a permutation in our group. Now, if we factor modulo enough primes, we'll get different conjugacy classes. And God willing, after we get enough conjugacy classes, we'll see that the group is big. So what does that mean? This is a typo. So each factorization type occurs with a certain density. This is not Dedekind. It's Frobenius, and then Chabatarov, if you like. So Chabatarov density says that there's a certain density of cycle types. Then there is a very easy theorem of Jordan, which you can read about in a complicated way in a paper of Serre in the bulletin of the AMS 10 years ago, that if you have a finite group and the proper subgroup, then the proper subgroup must miss a conjugacy class. So now we're cooking with gas, because you see, given that you use Chinese remaindering essentially to see that each primes are independent. So we take a polynomial, we factor it modulo many primes, and then the probability that we miss a cycle type goes to 0. And that's van der Waarden's argument. So van der Waarden used a very simple sieve method, and he proved the result of this form. So you have the probability of having Galois group which is smaller than the full symmetric group is n to the minus some power, which is a function of d, and as d goes to infinity, this quantity actually goes to 0. It's like something like 1 over d or something. But still, for any fixed d, you know that the generic case is Sn. And of course, number theorists like sieves, so they kept hammering away at this method. And I think the next big advance was by Pat Gallagher in the late 60s. And he got something like this, n to the minus 1/2 plus epsilon, which I think is, with sieve methods, that's pretty much usually as good as well as it can do. He did the large sieve kind of thing. And then there's been more work by this guy, Rainer Dietmann, who I think got n to the minus square root of 2 over 2 or somewhere. Anyway, so sieve methods get you somewhere, but not apparently to the truth. And plus, they're complicated. Large sieve is hard. There are people like Kowalski who make a good living sieving for years on end. Okay, so we use a primitive method, which gives better results. So the warm-up, which is also actually a result due to van der Waarden in the original form, is forget the Galois group. Let's ask the simpler question: what is the probability the polynomial is irreducible? I mean, certainly to have a Galois group Sn, which should be irreducible, so that's a good place to start. So we use the most primitive method possible, which sort of comes from a computational point of view. And I have to say that I learned to think this way because I spent a lot of time working on computer algebra. And my first mentor was this guy, Richard Zippel, of the Schwartz-Zippel fame. He was a very smart guy, who I think spent some time in Israel, actually, starting a private university about 10 years ago, which I didn't think happened. Anyway, so you just think of it in the most constructive way possible. The fact that the polynomial is reducible means that you can write it as a product of two polynomials. Okay? Think of the coefficients. Then each coefficient of the original polynomial can be written as a quadratic function of the two sets of coefficients, which call them b and c. And so we have a system of equations and a bunch of unknowns. In this case, the degree is d, or n, actually. We have n equations with n unknowns over the complex numbers. This will always have a solution. This is a good thing, because if it didn't, then the fundamental theorem of algebra would be false, and then we would all be in deep, deep trouble. And would have to start driving taxis for a living, and who would want that? But luckily for us, so that means that over C, every polynomial is reducible, something we all knew. But we don't want C. We want Z, or as my sometime colleagues and Santanders would say, Z. Okay, why are the integers different from complex numbers? Well, that's a deep philosophical question that I won't go into, but in this case, we'll show by example how they're different. Suppose the constant term is 1. I mean, it could happen. Actually, when I started thinking about these questions, I was actually thinking about matrices. And the matrices I like are in the special linear group, so then the constant term is 1 for the characteristic polynomial. So that's how the whole thing started. So then you see the coefficients of Q and R, which we call B and C, even though it wasn't defined, because I was writing this last night and no sleep. They're either both 1 or both minus 1. So there are only two possibilities. That means that we have, because the constant term is 1, we have lost one unknown. Right? But we've lost two of the parameter variables. So suddenly, our variety of reducible polynomials is of codimension 1. So now we're done, right? And now by Langevin, if you like, actually, people always say Langevin, but actually I think the result we need is a very primitive version. I think it's like the first lemma in Langevin, and I think it takes about 3 lines to prove, but whatever. Everybody says Langevin, so I'll say Langevin. So the probability that the polynomial is reducible then, and its constant coefficient is 1, is of order 1 over n. Easy. Well, okay. It's like at this point, it's like I'm somehow reminded, perhaps because of the aforementioned lack of sleep, of the comment in of a story in Mathematical Miscellany of Littlewood, because the teacher says, let x be the number of sheep, and the student raised his hand and said, but what if x is not the number of sheep? So similarly, suppose a0 is not 1. Then it seems like this method doesn't work, right? Well, that's sad. Well, what do we do then? Well, then we make it a little bit more subtle, because we say, well, it's true that b0 and c0 don't have to be 1, but they do have to divide a0. Okay? So for each factorization of a0, we can use the previous method. And the question is, how many factorizations are there? Well, the answer is, we don't know. It could be a lot. But we know, and this is a result of Dirichlet, it's Dirichlet's hyperbola theorem, that the average number of divisors from numbers between 1 and n, or minus n and n, if you like, is logarithmic. It's very easy. If you want error terms, it becomes slightly more difficult, but even then, it's not difficult. It's logarithmic. So we just sum over all the factorizations, and then we see the probability of a polynomial in the set of bounded coefficient polynomials being reducible is bounded above by O of log n over n. So the question is, how sharp is this? Now you notice that it's not very unsharp, because clearly there's a lower bound. What is the probability that the polynomial is reducible? Well, I'm sure everybody in this room can come up with a family of polynomials which are reducible, namely those with constant term 0. So the probability of having constant term 0 is 1 over 2n. So we're off by at most a log term, right? But log terms, I mean, especially those of us, and that doesn't include me, who are number theorists, care deeply about log terms. They even care deeply about log terms, which luckily we don't have any of here. So what's the truth? Well, so first, look at polynomials which have a linear factor. That turns out, I'll jump ahead, turns out to be the dominant case. So if the linear factor is x plus d, you just write down the equation for a's and b's, and I mean c's are, c0 is d, c1 is 1. So we only have b. The what? Yeah. That's a common problem. Think of this letter as something else. Call it F. Sheep, yes. Well, no, I mean, actually, I was going to say E, but that's another story from Littlewood, where somebody's defining a polynomial of degree, I think, 5, x to the 5th plus ax to the 4th, blah, blah, plus dx plus e, where e is not necessarily the base of natural logarithms. But could be. So here it couldn't be because it's an integer. And it's a simple computation in geometry of numbers, which I give to you as an exercise in case you get bored, that the covolume of this lattice is d to the degree minus 1. Okay? So then we just sum over all possible d's, and if d is big, I mean, if n is bigger than 2, then the sum is bounded. Actually, it's some zeta value, which we know what it is. And if d is equal to 2, then it diverges logarithmically in n. So that means if you look at the set of polynomials which have a linear factor, then the number is, the probability of having such a property is decays linearly for degree greater than 2, and decays like log n over n for degree equal to 2. So this is the truth. This is now not an estimate. You can actually find constants. I mean, we did find constants.
Sorry, can you say more how you can get from bullet point 2 to bullet point 3?
Yeah, because you just sum over all possible d.
Oh, I see.
Right? This is just a zeta value. When n becomes large enough. That's all. And now the question is, okay, so these are the ones that have a linear factor. What about the ones that don't have a linear factor? Well, I should say, what I'm about to show in the next slide is a little too fancy. I mean, again, mankind, in its infinite wisdom, has computed this. And yes, you can prove that this is a grows of lower order. There's a paper by, I think, a guy called Kuba, some Slovak guy, and the paper appears in like the Slovak Journal of Mathematics, of which is the only paper I've ever seen. But whatever, it's correct, it's fine. But why are the other? We want to understand why the other cases are subdominant. And for this, the way I think about it, and you might think of it in a different way. So what should be true is that if you look at the reducible polynomials, if you look at the variety of reducible polynomials, they should have no linear hypersurface component. That should be obvious, but I'm not sure why it is. So there's no linear condition on the coefficients which guarantees that the polynomial is reducible. That's what you want to say. And once you have that condition, there is PILA'S theorem, which comes from Bombieri-Pila, which says what? So you get this result, n to minus. With a linear term.
So you're taking away the constant term.
We're looking at decompositions with no linear factor. So if the constant term is 0, yes, it's reducible, but there's a linear factor. So we want the next. So yeah, in that case, there is a linear, of course. So the being divisible by x plus d is a linear condition, which is why it's a dominant term. But the other ones are nonlinear, and what PILA'S theorem says is that an irreducible variety, I guess absolutely reducible variety of degree d and dimension n has at most h to the n minus 1 plus 1 over d plus epsilon. The epsilon is actually explicit in PILA. It's something like x of square root of log of h times d or some stupid thing. But in any case, it's epsilon. And then once we get rid of the hyperplane pieces, because notice for hyperplane, this gives no saving over the obvious thing. Well, this gives a lower order growth than the dominant term, and now we're done. Well, that's good. So again, there may be a different. I mean, obviously, in this particular case, there's more concrete ways of computing this, but this is a philosophy that will talk about some of the conjectures that are coming. So, okay. Now we'll go to Galois groups. So for this, there are a number of ways of thinking about this. And again, we want to think in the most stone axe way possible, going back to, I don't know, Legendre, Lagrange, Vieta, somebody, right? We think of resolvents. So if you have a subgroup of Sn, then we would like to know when is it true that the Galois group of our favorite polynomial is a subgroup of that subgroup G. So for this, I mean, it's not defined on these slides because, again, I was writing them in a rush, but I'll tell you in words just to confuse you because these things are actually easier done on the board. What is a resolvent? So first of all, for every subgroup of the symmetric group, we say that a function belongs to that subgroup. A function of many variables, of n variables, belongs to that subgroup if it is invariant exactly under the elements of the subgroup. So it's easy to see that such thing exists. It's just the product of xi to the I works, for example. It's not the only one, but and then you look at the orbit under the group. Okay, and then the resolvent of our of a group is just a product of x minus the look at the function of the roots. Is there a yes? If memory serves, it looks looks like this. It's a product of x minus pi of f of R1 through Rn. So f is a function belonging to the subgroup, and pi ranges over coset representatives of G. It's a subgroup. It doesn't have to be maximal. Just our Galois group is a subgroup of G. If first we'll write down this resolvent, Q sub G of x. So again, this is a function belonging to G. This is a sum. So the Galois group of P belongs. So R1 through Rn are the roots of P. Is a subgroup of G if and only if this resolvent has an integer root. Okay? That's easy to see. And actually, you only need one direction. So Galois group of P is a subgroup of G if and only if Q sub G of GP of x has an integer root. So again, this must be classical, but the reference I know is I think about 1970 PhD thesis of a guy called Stauduhar. This thesis actually is very well known in the computational community because that's the best way to compute Galois groups known to man. Yes? Yes.
No, that's known much better.
I'm sure, but I mean, it's like the Galois resolvent or something.
Yeah, I don't have a reference, but
yeah. Anyway, I think Stauduhar in his thesis doesn't cite anybody, yeah. But again, Stauduhar is close to my heart because he was a Stone Axe guy. Clearly, you read his thesis, he clearly hasn't tried anything. He just figured it out and it worked. Okay. Has an integer root. Very nice. So now what? Well, first thing you observe is that the coefficients of this resolvent polynomial, that's not hard to see, they're polynomial in the coefficients of the original polynomial. That's easy. So, suppose you have an integer root. Well then, what are the possibilities? One possibility is that this resolvent is identically 0. Certainly, the 0 polynomial has many integer roots. But that's impossible because we know there are some polynomials with full symmetric group as the... I mean, take G to be some group which is not a full symmetric group. We know that there are some polynomials whose Galois group is not a subgroup of G. Excellent. Could it be... Now we look at just as with the reducibility, we look at the constant term. Maybe the constant term is 0. But if it's 0, then again, everything has an integer root, 0. So that can be. Therefore, it is not 0. And therefore, we have an equation of the form q of some integer is equal to 0. So q of rho equals 0. But what does that mean? Suppose the coefficient of these things are a0 through an. So this q of p is equal to sum of ai rho to the I. We know that a0 is not 0, as we just discussed. So it means that a0 is the sum, as I goes from 1 to n, of ai rho to the I. But in particular, it's divisible by rho. So rho has to be a divisor of a0. And now we use the same argument as before. And now we have to see, now we look at we can't use Dirichlet's theorem because now instead of looking at divisors of just n, we look at divisors of some polynomial in n. But again, through the magic of analytic number theory, that's not very hard. And instead of a log term, we get log to some power. So that means that instead of, so we get the correct exponent. We get O of log to the k for some k, which depends on the degree. Actually, if you really are careful and see what k is, it is insanely high. It could be like, d factorial or something ridiculous. Because it has to do, like if you look at this, you just have to look at the degree of the polynomial you get as a constant term, and it has to do with the index of the maximal subgroup, because we only do this for maximal subgroups, and some maximal subgroups have very high index. So you get something like log n to the d factorial over n, which obviously from a practical standpoint is totally worthless. But as again, since we can now pretend to be analytic number theorists, all we care about is asymptotic growth. So it's all good. It's the right exponent. It's O of 1 over to the n minus 1 plus epsilon. So this is, except for the epsilon, that is the sharp result. Why is it the sharp result? Well, because the probability of 1 over n that it's reducible. So you certainly can't have better than that. But now the question is, well, again, what is the truth? That's a really interesting question. And the answer is, just as before, the dominant term is exactly things whose linear factor. And it is my belief, which I can prove, of course, that that the probability of any transitive Galois group should be much lower. It should be like 1 over n squared. And the reason I believe this is because, again, I cannot think of any hyperplane condition that would assure that the Galois group is not Sn. There's no linear condition on the coefficients. Now, we should be careful. There's a difference between hyperplane and linear. So here's a linear condition which assures us that the Galois group is not a symmetric group. Suppose our polynomial is reciprocal. So f of x is equal to f of 1 over x times whatever x to the whatever it is, n, or 2n, or whatever it is, right? So these polynomials are much beloved by many of us because, well, they're characteristic polynomials of symplectic matrices, and they come up in Lamar's conjecture, and they're just everywhere. Well, anyway, this is a linear condition of the coefficient. It just says that the nth coefficient and the n minus dth and dth coefficients are the same. And the Galois group of a general polynomial of this form is not Sn. It is the hyperoctahedral group. It's a Reith product of C2 and S. Well, if this degree is 2n and Sn over 2, if you want. Right? So, not the symmetric group. So, yeah, there are linear conditions that tell us something about the Galois group, but this is not the condimension 1 condition. So, there's something tricky going Another thing that is relevant is that the results of SD Cohen, Steve Cohen, which says that if you look at polynomials, so I said before, I mentioned the van der Waals result that says that generically the Galois group is Sn. Cohen strengthened it by saying you can fix your favorite coefficient, and that's still true. Actually, Cohen proved much more. You can fix every coefficient but one, I think, and it's still true. But two? Yeah, okay, two. In fact, we'll see a counterexample to what I just said. Yeah, you have to be careful because you have to fix coefficients in certain ways. For example, you can't fix them in such a way that your polynomial is polynomial of x to the k. So you have to be a little bit careful. But if you do it, or you can't fix the constant coefficient to be 0. That would be bad. But other than that, it works. So anyway. So if you believe that other than these stupid cases there's no hyperplane condition, then part of the point is it should get rid of all this log to the d factorial term because it drops you down below linear. But I don't know how to do it at the moment. Is that the same? So now the question is, okay, this is all kind of that's very nice. We know that the generic case is Sn, but the interesting question, of course, is we have the collection of all subgroups of Sn. How are they distributed as Galois groups? So if you want to be overambitious, it is the much stronger version of the inverse Galois problem. We don't just want to know which groups are possible, but how possible are they? Well, in that generality, of course, I have no claim to know anything Sarah doesn't, so, But still, it's a question. And for small degrees, we can just see what happens. So when one is young and stupid, one believes that, of course, what is the biggest subgroup we can have of Sn? Well, it's An, of course. So you would think that An would be pretty popular among Galois groups. The answer is no. It's actually extremely unpopular. And the heuristic reasoning is the following. A Galois group is a subgroup of N if and only if the discriminant is a perfect square. Everybody knows this, I assume. And if not, just believe me. So the size of the discriminant is about n to the n, if memory serves. So in the usual number theory heuristic is that about square root of those numbers are squares. And there should be some kind of a distribution somewhere. And so the probability that your Galois group is a subgroup of An should be like O of n to the minus n over 2, which is very, very small. How should you be able to see how small it is? It means that if you take a polynomial of degree 8 and try to compute Galois groups willy-nilly, you will never see An. Ever. Because your computer isn't fast enough to generate that many. So An is very unpopular. Okay, well, that's interesting. Actually, again, my introduction to this whole set of problems was when the Earth was very young, and I was a graduate student in Princeton, and the Earth was so young that Dick Gross was a junior faculty at Princeton at the time, and had the misfortune of teaching me algebraic number theory. And he was talking about some experiments he did with Zagier, and they were working on the inverse Galois problem, and they were trying to find a polynomial whose Galois group was the MATGES group, I think M11. That was the first interesting case. So they said, well, Zagier did a lot of computing. He had craze. He was a macho computing guy. Just generate some examples and see what happens. Well, nothing happened. Because everything they generated had Galois group Sn. And even the An they couldn't get, much less the MATGES group. And now we know why. So I was very impressed by this at the time, and I never forgotten it. And
did anybody construct an example when Galois group is An sims?
M11, you mean? An AN is very common. I mean, they're families of AN Galois groups. I mean, you want a family where the discriminant is a square. You can write down certain, I think even trinomials, where you can compute the discriminant explicitly, and you can just massage the coefficient so it's a square. So, yeah. AN is easy. M11 and M12 were done, I think, by Mali, but I'm not sure. Almost immediately after Gross and Zagier failed miserably. It was basically like the same year. And that's probably why they stopped. Not because they were proud people. I'm sure they would have kept working, but then somebody just did it using pure thought instead of computers, which was really embarrassing. So yeah, I think I was talking to Lior about this. I think M24, which is the one remaining sporadic group, I think is still unknown. 23. There's still no unknown example, I think. Right. And again, you actually have to think, which is unfortunate. Personally, I try to avoid thinking as best I can, but all right. So how are they distributed? Here's some experiments. For n equals 4, let's be simple here. So I did an experiment this last summer, actually, because I was looking, I think, on Math Overflow or something, and then there was a nice algorithm to check if to compute the Galois group of quartexes. Well, okay, let's do it. So this is what you get. S4 is hugely dominant. Reducible. So again, I think for cubics, you can do this computation essentially by hand. You don't need a computer, because the Galois groups possible are the trivial group, Z2, Z3, and S3. And I think it's not very interesting, but you can probably compute. It's a Diophantine question, which would be actually an interesting, I think, master's thesis project to check. So, food for thought. But here, so if it's reducible, then almost certainly the Galois group is S3. Because again, you have a linear factor, right? And the rest should be reducible. D4 is very common. But again, if you look at how common, that certainly lends credence to the belief that it's 1 over n squared. And then A4 and V4, the Klein 4 group, my conjecture is that they're equally probable. And you seem to lose another factor of 40, almost exactly, right?
Can you do the opposite way, just with 4 and 40, assume that all subgroups have equal probability and look at the distribution of coefficients instead?
Well, you're talking about an experimental? How would you do the experiment?
I don't know. This is
No, so yeah. So here's a question, right? Suppose you want to generate only polynomials with Galois group V4. How would you do it? I mean, for 4, I don't know what the condition is. It's something not.
Actually, here I think that for V4 it's probably doable because it defines an elliptic curve,
Mm-hmm.
and then you know plausibly what are the integer or rational points, so maybe you can generate them.
Yeah, you might be right.
In case n equals 4, but in general that's hopeless, I guess. Even for n equals
Yeah, no, no, I understand. That's a good question. Just for 4.
yeah.
Yeah, just to generate. Yeah.
Why do you think that they're equally probable?
Well, just numerical evidence. I have no other evidence.
But if you know that the discriminant is a perfect square, then most probably it will be A4, no? This naively. It could be the maximum possible.
Well,
And V4 is inside of it.
I don't know. But exactly, I don't know. You might, but maybe if you took the coefficients to 400, maybe you'll get a different result. But somehow, at worst, I'm going to grant you a log term, but maybe not even. And here's an actual theorem coming out of this experiment, which may not be interesting, related to this cone thing. So you look at the general quartic, but not general. A, C, and D are -1, 0, or 1. And B is arbitrary. So the Galois group is never A4. So that I view as a circumstantial evidence for the fact that A4 is very rare. By the way, I should say, this heuristic I mentioned about the discriminants, what is really depressing is how far number theory is from proving anything like this. So there are papers by Heath Brown and Moose and Squirrel and various other people, and they have trouble getting linear saving. So instead of probability minus n over 2, n to the minus n over 2, if you're really lucky, you can get n to the minus 1. But they can't even get that without the assumption. I mean, they use various Katz things, and so they have conditions on the polynomial, like the main homogeneous term is non-singular, which I guess you need for some of these they type results, Deligne type results, but it's nowhere near the truth. And unfortunately, discriminant doesn't even satisfy that condition. So for the discriminant, essentially nothing intelligent is known, but we'll see something in a second. So for
say it's never A4, can it be V4?
it is never a subgroup A4 or a subgroup thereof.
So the discriminant is never a square.
Never square.
This is empirical?
Huh?
Is this empirical?
That's a theorem.
So it's basically 27 hyperelliptic curves, and you're showing that they don't have a point.
Here, well, you can check that the discriminant is often negative, in which case not a square, and in other cases you can tell that it's not a square. So it's not very hard. So okay, now degree 4 actually has been studied in a slightly different model, which we'll mention a couple of other things. So I'm not sure what the history of this is. I was talking to Ellenberg about this, and even then I couldn't figure out what the history is. But it's known that for degree 4, if you count fields by discriminant instead of by coefficient, then it is not true that 100% of the groups is S4. And Mahler has some heuristic which tells you exactly what the density is of the next one, which, not surprisingly, is D4. And I think Ellenberg can do it in the functions field case. I'm not sure what exactly the status of this is. He showed it? Okay.
Bargava proved it in the number field case, right? Yeah.
Well, what did Ellenberg do then? Huh?
Degree 4.
D4. No, we don't think about degree 4. Yeah. So again, not surprisingly, D4 is the next highest. Why there's a qualitative difference between the counting by coefficient and counting by discriminant is not clear. I mean, again, I was talking to Ellenberg about this yesterday. He's in Jerusalem. Well, actually, right now he's in the plane, I think. But yesterday he was in Jerusalem. And his argument is, well, these are different models, so why should the results be the same? Fair point.
Higher than S3.
Huh?
D4 is higher than, is larger than S3.
No, S3 is by far the. Oh, I think there. Then when you look at discriminant. So this is the minimal polynomial of something. So the reducible case doesn't come up in the discriminant. Yeah. So that's one difference, but not a huge difference. Okay. And here's another way, which is how I came to this. It's not directly relevant, but might as well mention it. If you look at characteristic polynomials of random matrices, here's a way to generate polynomials. Look at random matrices with large coefficients and look at their characteristic polynomials. And so then, using sieve methods, one can show again that the characteristic polynomial of random matrix SLN has Goa group Sn, and proof is by sieving. Actually, yeah. So this is by the random product of matrices, or just to look at the matrix of bounded norm, or bounded Frobenius norm. The result is true by completely different methods in both cases. The distribution will be different. Oh, and I should say that it's a result of, I guess, Kowalski and somebody and Zivina. That, I mean, it's essentially the same argument. That for a semi-simple group, you don't get the Sn, you get the Weil group of the group, and in particular for the symplectic case, you get the aforementioned hyperoctahedral group. But here's a curious observation, again, coming from numerical experiments. Look at random products of matrices and compute long random products. Compute the characteristic polynomials. What do you see? And what you see is that with probability 1, the eigenvalues are all real. Try it. Try it at home. Now, this is a theorem, and not my theorem either. It probably goes back to Furstenberg. The argument is very simple. If you look at matrix products, you have ping pong. So in particular, this random product is a proximal transformation. So it has a single eigenvalue of maximal modulus. Well, if it's a single eigenvalue of maximal modulus, it must be its own complex conjugate. Therefore, it's real. Okay, so now we have one real eigenvalue. And now we do the thing which, again, probably goes back to Archimedes or something. You look at the action on the exterior powers. These are the standard action on exterior powers. Those are also proximal. And their top eigenvalue is the sum of the top k eigenvalues of the matrix. Therefore, those are real as well. And therefore, you're done. But this is very weird, right? So it tells you, in some sense, in the matrix sense, a random polynomial is totally real. So I'm not sure if that's true in any other context or not, but because the ping pong thing is very specific to the matrix case. But
It's also specific to this model of random integer matrix being a product.
so here's, well, not exactly. So let's say you look at the bounded norm thing. So it is not true necessarily, I think, that if you look at the Frobenius ball, that a random matrix will be proximal. Actually, I'm not sure. It's not going to be very proximal, but it might be proximal. So what is true by Fuchs and Riven is that if you look at a slightly modified ball, so see, the thing is that bounding the Frobenius norm is not a very symmetric operation, as it turns out. What you'd like is to bound the Frobenius norm of the matrix and its inverse. There must be a name for this object, but it comes up. So if you pick things uniformly at random from that symmetrized ball, then the same statement is true. Then they play ping pong, and so you'll have the same result. So this is somewhat universal. How universal, I'm not sure, but at least it's somewhat universal. And again, I'm not sure if there's any model of polynomials which doesn't involve matrices where this is true as well, but you can check.
What are generators? What do you mean by generators?
So SL and Z, or Z, depending on how you think about it, is a discrete group. It's finitely generated. Pick your favorite generating set. I don't care which one. And just look at random long products. Yeah. And then see what happens. So actually, the same statement is true for, they don't even have to generate SL and Z. They can generate, as a risky dense subgroup, get the same result by, I guess, Goldshade Margulis. And there's a good application to all this. Actually, it's risky dense. If I give you a subgroup of a SL and Z given by generators and I ask you if it's risky dense, how do you tell? Well, here's the cutest algorithm I personally know. Compute a long word in the generators and compute its Galois group. So it is either Sn or not. If it's not Sn, you say no, the group is not risky dense. If it is Sn, you compute another long product. So you get two elements now. Either they commute or they don't. If they commute, the group is not Zariski dense. And if they don't commute, then it is. So I'm cheating a little bit because some of these cases are non-probabilistic and some are probabilistic. So it's conceivable that if you take a very long product, then the Galois group is not Sn, and the subgroup is still Zariski dense, but the probability of this goes down exponentially with the length of the product. So, since life is short, you can So yeah. Oh, and computing Galois group is hard. Actually, interestingly, I don't know, there's no computer scientists here, but I've never seen any results on the complexity of computing Galois groups. But computing that the Galois group is the full symmetric group is easy, because you just factor it modulo a bunch of random primes, and then you look at the conjugacy classes, and then you know that you don't have to factor very many primes to make sure that these conjugacy classes always generate the whole group. There's a recent paper of Yuval Peres and Pimentel and myself quantifying this, but this has been known for many decades. So that's the simplest way of checking if it's a probabilistic algorithm to compute that the Galois group is symmetric. There's also a deterministic algorithm, which is polynomial time, which is, I can explain, but don't have time probably. But it has complexity of something like the degree to the 40th. So it's a polynomial, but not one that you particularly want to deal with. Actually, I have 2 minutes. I'll explain the algorithm. If you have a polynomial, so find its companion matrix, then it'll, just as before, you can act on exterior powers. And so look at the actions on the first, second, third, fourth, and fifth exterior powers. If the action is irreducible on all 5 exterior powers, that means that your Galois group is 5 transitive, and therefore it's SN. And you check transitivity by factoring. So it reduces the polynomial factoring. But the problem is that the 5th exterior power is going to be of high degree. So anyway, on this very uplifting note, I'll stop and